3. Yeah, chapter 3, PowerPoint 51. If you ever forget which one we're on, if you go onto that Google Classroom, there's that Sheets. That's the class schedule. And that has the exact PowerPoint slide I'm going to begin on, and then what I ended on for that day. Yeah. Which is the one I ended on the previous day. Public service announcement while I'm here is don't forget to turn in your lab notebooks. That's lab notebook A with the experiment 3 stuff. Okay? Lab notebook B is the one you'll be working out of for a while, and that's going to be the experiment 4 that we're doing this week, right? That's because I'm going to hopefully turn these around fairly quickly and get them back to you. Okay? Does take me a while to grade once I have them all though. Okay. Yeah, I'd rather a lab, please. Yeah, thank you. Because okay. So we have the cyclopropane. We're using this to demonstrate our angle and torsional strains. Which side is angle strain again? Which of these two things is angle strain? Yeah, this is the most clear representation of angle strain probably. Though technically both kind of show you an angle strain to some degree. Okay. The angle strain actually occurs because you do not have proper overlap of your orbitals. So you can think of it a bit like this. What would happen if I have two spaces that could contain something and then I don't overlap them properly? Well, I have less space to contain that, right? And so when I put those two electrons in there, they have less space that will pull these two nuclei together, won't they? Okay? And that means you get more repulsion force versus the forces bringing them together, right? Okay. Okay, so this right here actually shows you how cyclobutane is actually not planar. So notice that in most of the, yeah. You did have a visual yes. And that's the one on the right side? No, it's going to be the next one. And this one. Okay. So this one's the torsional strain if this was planar, right? And what you notice here is that because they're overlapping, you're actually getting the highest energy state, aren't you? Okay? Because of that overlap. Normally you would, okay, so do you know what torsion is? Or torque? Yeah. Literally a rotation, right? Okay. And so torsional strain from not being able to rotate, right? Because it's trapped. Okay? Oh, yeah, you did the Yep. That's exactly right. We're trapped, right? Because we have a ring. Yeah. So we have the hydrogens trapped in place and they can't rotate that much. Now, this would be planar where they're directly overlapping each other if you just line up your two hands. But what if you notice with your two fingers connected, you still have a little bit of wiggle room, right? And that's the same for a four-membered ring. It still has some wiggle room, okay? And so what happens is instead of having a four-membered ring where everything's lined up exactly over top each other, you're going to get what little torsion it can afford, okay? This will actually also relieve a little bit of that angle strain as well. And so four-membered rings, you get the bent conformation. See how it's bent? Like taking a piece of paper and literally just bending it along the corner. Yeah. This actually shows you here the Newman projection, which is the easiest way to see torsional strain. Okay? So this is down one of these bonds here. it actually doesn't matter which one we are, they'd all give you something similar, okay? Just depending on your perspective. If you looked at down this way or down this way, okay? And so you see that they've actually offset this, so it's almost eclipsed, but it doesn't quite make it there, does it? Okay? So it's not quite eclipsed anymore, and we can't quite get to staggered, can we? So it's almost staggered, but not quite, right? So it partially relieves that strain, but not fully, and that's why the four-membered rings are not stable, okay? There's very few four-membered rings that are stable. If you put anything on them that's fairly large, they become much less stable to the point where, like, if they got exposed to air, they'll blow up, okay? Okay, anyways, they combust very easily. Why is the three-membered rings particularly unstable, by the way? Again, how many points define a plane? 3. So if you only have 3 points, 3 atoms, it automatically is in one plane, isn't it? Yeah. 2 points automatically would be a line, right? And 1 point is 1 point in space. Has nothing else. Okay, you can't have any bends in 1 point, right? Can you have a bond angle with 2 atoms? No. You can't make an angle, right? Because it takes 3 points to make an angle. You only have 2 points. It's always a line, no matter what you do. Okay? Okay, anyways, these can't do any sort of twisting or rotation or anything. A three-membered ring is always in a plane. Okay? You literally can't do anything else by definition. Right. This is the cyclopentane. It actually has a couple conformers. The flap is one of the more stable ones for most cyclopentanes. Okay? This is the flap. It looks a bit like an envelope with the top bent in. Okay? Okay. Some people would actually call it an envelope conformation. There's a couple other conformations that actually can be stable depending on the substituents, but that's not here or there. That's a more advanced thing. Anyways, you can see that we're actually getting this closer and closer to being its sort of ideal staggered conformation, aren't we? Okay? Can you see that we're getting that? So it has enough room that can twist properly to get a nice staggered conformation of those hydrogens coming off here. And it also is getting closer to the ideal 109.5 degree angle of the tetrahedral, right? And so our five-membered rings are pretty stable. Okay? Typically, a 5- and 6-membered ring is considered the stable rings. Okay? They're about the same stability as being a straight-chained alkane would be. Just a little bit off. Okay. Here's the 6-membered ring. Typically, the most stable conformer for the 6-membered ring is, what's that? A chair. Looks like a deck chair. Can you see it? Yep. There you go. So that's the chair. This would be the Newman projection, looking down 2 of these bonds. And you see that if you rotate this a bit and put that as the one closest, this one also ends up being closest to you. And you can look down that bond and that bond. Everybody see that okay? Okay. Really do tell me if you can actually rotate that in your head and see it. Like I have... Full disclosure, I've had my IQ extensively tested and actually was given a scholarship to go to college when I was 13, but that was actually turned down by my parents because there was a bunch of stuff going on. So, I have like an IQ 180 in this. I can fully rotate everything three-dimensionally and view it as if it's an object in front of me. Okay? So, do actually tell me if you can't or you're like, what in the hell are you talking about, Dr. Clausen? Because to me, that's not hard. Okay? Okay. All right. In fact, if my memory wasn't so bad, my IQ would go up a lot. But my memory is. It's slightly above average. That's it. My short-term memory. My long-term memory is better than my short-term memory. Which is so weird, by the way. That's why, like, the next day I'm like, I remember that now. Okay, so again, this is your Newman projection. You're looking down these two bonds, and you can see that it's actually pretty much a staggered conformation, right? By the way, this same Newman projection is the same for all of these different carbons. You just have to rotate the molecule around, okay? And it will match up like this across pretty much the whole thing. Like, for example, this one right here and this one right here can also be a chair, the top and bottom of a chair. Can you see that? Like, that's the flap downwards. This is the body of the chair. This is the flap upwards. Okay? Because we don't have anything else unique on it. So they're all degenerate to each other. All the carbons are. Okay, anyways, does anybody have any questions about the chair conformation? Keep in mind, these are not the only conformations possible. I'm only going to be talking about the most stable conformations for most of these. Some of these we'll talk about two conformations, but there are other conformations. For example, the 5-membered rings have a conformation that's called twist, where basically it goes up, down, up, down, up, down. Okay? And it looks like somebody took the ring and just sort of twisted it. Right? There's also the envelope conformation for the 5-membered rings. Anyways, I did a bunch of rings for my dissertation. If you want to see 800 pages of research on rings, I can loan you the dissertation. It has all the molecular structures and conformations and all that, and with different substituents. And I had to publish it in 2 books. They're the size of the small textbooks. It is just stupidly long. Just unnecessary. But I did all the research, so damn it, I was going to put it in. So this right here, again, is just the summary of the chair conformation we just talked about. It's basically the same sort of angles that you would see in a straight chain. This right here is the boat conformation. Can you see the boat shape? Ooh, it looks like a nice boat.
I had a question on the last slide.
What's up?
So that means it's tetrahedral.
Yeah, they're all tetrahedral.
Okay, gotcha.
So the best way of thinking of these is anytime you have a single bonded carbon, doesn't have any double or triple bonds in it, it's always going to be tetrahedral. Okay? The only time it's not tetrahedral is when one of the p orbitals is consumed in something else. Now, in the rings, when you have a 3 or 4-membered ring, or even 5-membered rings, and even to a small degree a 6-membered ring, what you're going to have is a tetrahedral shapes for those carbons, but they'll be perturbed. They can't go all the way out to the tetrahedral 109.5. They're going to be a little bit bent. Okay? And that's a bit like the tetrahedral electronic geometry. Do you guys remember the difference between like molecular and electronic geometries? Okay, so like water has an electronic geometry or an electron geometry that's tetrahedral. Okay? But the molecular geometry is bent. And remember that angle gets smooshed. It gets a little bit smaller, right? For the hydrogens, because those lone pairs take up more space. It's a bit like that. It's tetrahedral, but it's a little bit off because of the shape does not allow it to expand out. That make sense? Okay, and you can have other things that affect this, by the way. For example, particularly large substituents, the hydrogen bond, or are polar, and so they'll be attracted. But we're not going to go that far into that stuff. We're just going to give you the underpinnings and the basics of it so that you can understand it if you ever go on. Yeah. By the way, if you're interested in that stuff, talk to me. There's a whole field that goes into that stuff. And it is like, there are 99 jobs for every one that's filled. So it can pay very well as long as you don't go into teaching at universities. Like my offering salary was 4 times my salary here for going private. So yeah, that was stupid of me, wasn't it? But I guess you guys lucked out. So yeah, take advantage of that. Anyways, this is your boat. This is actually the twist boat, by the way, though there are other names for that. This is actually not a very commonly used name, but it's the one your book uses. So, anyways, this is typically less stable than your chair would be chair conformation, though there are substituents you can have on here which will make it more stable in comparison. Everything can be relative, by the way. One of the things to look at here is, see these flagpole hydrogens? They're the hydrogens that are on like the bow and stern of your boat. Okay. Look at how close they are. Can you see that? That the ring comes back together, and so these start overlapping again up there. Yeah. And so you're going to get steric hindrance from those. Okay? That's what typically makes this less stable than it otherwise would be. Okay, right here we actually can see the energy diagram. Again, this is potential energy. Notice there's only one chair conformation for this because it is symmetric, right? Okay. So when one flaps down, one flaps up, you can just rotate it 180 degrees and you get the exact same thing. There is no difference at all. Okay? Okay, there's actually 2 twist, 2 half chairs, and 1 boat conformation. You'll notice the boat conformation is actually not a stable conformer. Okay? That's actually a transition state. Can you see that? And that's because the twist boat conformations here are lower energy. So if it does end up as the boat conformation, it's going to twist and fall down into that lower energy, right? Okay. That's what a transition state is, by the way. It's just a configuration, a conformation that is not stable in comparison to stuff around it. Okay? It's kind of like, what is a hill? Well, the hill here is lower than the low points in Montana, right? So we have lower potential energy on our highest mountain here, right? Than the low point in Montana. Okay? Remember, conformations and transition states are always relative. Okay? Okay, these are the half chairs, by the way. They're the high energy transition states. They would be the slowest thing to get through. They would take the most energy to get through. By the way, this is actually pretty easy to trap in the chair conformation because there's a large energy difference here. So if you keep this cool, you can actually get it mostly chair conformation, which is interesting. Anybody have any questions? Are you making some of these connections? Okay, like all energy difference diagrams actually show you population distributions as well. If you have more energy, you can have more stuff jump up into the high energy forms. If you have less energy, i.e. lower temperature, you get more stuff trapped in low energy forms, right? Anybody know what happens if you take the temperature down really fast? No? Anybody know how you make like amorphous metal? No? You freeze it really fast. Okay? So if you freeze something slowly, if you cool it slowly, then it has time to jump over these energy barriers and then collect in the lowest energy forms. Okay? And then it can't get back up, right? It's the best way to think about it. So if you take it and just, degree by degree go down, then it has enough energy to jump out of here, but it's not going to have enough energy to jump back, right? Okay. But if you take something and just go down really fast, and so boom, we're down to freezing dry ice or helium or something really low, okay? Nitrogen, liquid nitrogen, then what would happen is we don't even have enough energy to get over this one. And so whatever populations we had at the time, they get frozen there, don't they? We can't get over any of the other energy barriers. Okay? And that's how you get like amorphous, where it doesn't have time to settle out into crystals. By the way, the same thing sometimes happen to you guys. That's why you always have to take stuff that you've been heating, cool it to room temperature first, and then put it on ice. Because if you take it down too fast, it can get stuck and not crystallize. Okay? You can also make supersaturated liquids and stuff from that, at least temporarily. Now, the axial and equatorial positions, these are going to be a little bit difficult for you to understand at first, but remember it is a relative position, okay? So axial bonds, these are going to be the ones in the red here. If you're good at pattern recognition, you may have already figured it out. These are going to be directed vertically, parallel to the axis of the ring, okay? So axial as in axial, like the axial poles of the planet, right? Okay. So they're going to be vertically directed in comparison to the ring, i.e. they overlap the ring. Okay? The equatorial bonds, the green ones, are going to be directed outwards towards the equator, that's equatorial, right, of the molecule. They're going to point outwards from the molecule. Okay? Can you see that? They're pointing outwards away from the molecule. These are abbreviated EQ for equatorial, AX for axial. I think the space filling diagram actually does the best job of showing this, how they literally come up and overlap. See that? So when you point straight upwards along the ring, what ends up happening is your hydrogens end up overlapping, don't they? See that? The space-filling molecule, how they're much more scrunched together for the axial red positions. The equatorial positions, because they're pointing outwards away from the ring, along the equator of that ring, they're going to be pointing away from each other more. And can you see how they're pointing? They have more space in between them. Can you kind of tell that? No? Yeah? Kind of? Okay, these are the equatorial positions. See, so this is the ring right here, right? Okay. So this is a point on the ring. Okay. The equatorial position points outwards away from the ring. Okay? And if you were to look at this, the axis of the ring points up and down like this. See that? And this would be the equator. Okay? Okay. So the equatorial point outwards along the equator. And they end up being more spread out because they don't have as much overlap. The axial point upwards along the axis. They're perpendicular to the axis. So they point in the same directions like your axis does. And that's then going to be these right here. Okay. Let me actually step back and make sure you understand axis. So has anybody ever spun football or seen a football spun?
Throw it or fire
Either way. So if you throw a football the correct way it spins along the axis. Okay? If you take it, put in your finger and spin it, what do? You spin it along the axis, right? So it doesn't really matter, it's the same thing. Okay? Okay, now many molecules are essentially football shaped, right? Can you see that this is shaped a bit like a football? It's oblong. It's flatter on one side, more lengthened on the other. So if you were going to throw this like a football, how would it spin? Along this, right? Yeah. So that's your axis. Perpendicular to that axis is axial, right? Which is these right here. And so they end up overlapping the majority of your ring's bulk. Can you see that? Because they jet out along the ring's bulk. Does that make sense? Did that help at all? Okay. Yeah, I think that's a better way of approaching it in the future. Okay. And then if you look at this, again, this is your axis for this ring. Right there. Yeah. And so equatorial is these ones that go along that. And so they end up pointing away from the bulk of your ring, don't they? Okay, there's two ways of looking at this in comparison to your axis of your ring, though you have to identify the axis of the ring, which for some people is challenging. Or there's the way of looking at it is axial overlaps the bulk of your rings, equatorial points outwards from it. Okay? They mean the same thing because of how you would figure out an axis, right? Okay, so this right here would be your chair-chair interconversion. So what we're seeing here is that we have here a chair. What's going to happen is one side of it will end up coming up and the other side comes down. This is how you interconvert between the two forms of the chair. Okay? Okay. Everybody see that okay? Fantastic. It's degenerate in this case because we don't have different substituents for the previous cases. We didn't have different substituents. If we substitute something different, like a methyl group right here, then it becomes different depending on the side, right? See the methyl group that's blue? Fantastic. Okay, so these are different. Right here, the methyl group is axial because that side is pointing upwards, right? So the methyl group ends up pointing out along the ring. Okay? You can see it has more overlap with the ring. You can even see it kind of almost touches those hydrogens, doesn't it? Okay? These axial hydrogens here. What do you think that's the most stable conformer? No. Yeah, you're going to have quite a bit of steric interference, aren't you? Okay. And so what happens is this has a conformation interchange. Okay? And to do that, it has to go through the boat, doesn't it? To change from one to the other, it has to go through the boat conformation. Okay? And that's going to be your transition state. That's that high energy state you have to go through. Then on the other side of that, you're going to end up with the other way, where 1 is pointing down and 4 is pointing up. Left side is pointing up, right side is pointing down. And that's going to cause your methyl group to be equatorial, which would be the more stable form, right? Can you see how this is jutting outwards now? And it doesn't have anything that overlaps very well with it, does it? Yeah. And that's how you can tell that's more stable. Lower energy, right? Does anybody have any questions about that so far? Very good. We're building it up, right? Slowly building it up. You can also think of this as talking about it as gauche, okay? So in the axial methyl right here, we can see that the methyl group that comes out over the ring, when it's in the axial position, is actually gauche to one of the carbons, isn't it? So if we were to look down that bond in a Newman projection, what we would see is that this methyl jutting out in the axial position on that ring is gauche to one of the ring's carbons, isn't it? See that? Which is typically the more high energy state, isn't it? Okay? One of the higher energy conformers. When it's in the equatorial position, what do we see here? It's no longer gauche, is it? It is now anti. You got it. Which is the lower energy state, isn't it? Okay? That literally was the same thing I just said, wasn't it? Like I covered it in one way, and then I went the other direction on covering it, didn't I? And so when you're talking about organic chemistry, you can basically approach it from many different directions and end up at the same result. Okay? That's one of the reasons why I keep telling you guys, this is a practice chemistry, okay? Just practice it because there's 1,000 paths to the same understanding, right? And I could, describe hundreds of those, but we don't have time. Even 2 of them took too long, didn't it? Yeah. So, yes. This right here is your diaxial interaction. So on the 1 and 3 positions, you get an interaction between your axial groups. So see these axial hydrogens there interact with that methyl. You can actually see this in the space filling very easily. See that? How these overlap? They almost look like they overlap, don't they? And so those will be repelling because they're negatively charged electrons. They're getting close to each other, aren't they? That's called the 1,3 diaxial interaction. Okay? And that's actually what you're seeing right here. And so that's the less stable conformer because it's higher energy. Why is it high energy? Because it has a 1,3 diaxial interaction, doesn't it? Okay? Okay. These are some common energy differences for various different axial groups here. So see the X here, that's a substituent. It's a variable that we can replace with any of these substituents, can't we? And so here we have fluoride, we have cyanide, chloride, etc. Okay? And what we can see here is that this is then the delta G. It's the free energy difference, right? That being the amount of energy difference that is caused by that interaction. Okay? Because here we have the axial conformer, here we have the equatorial. Right? In the axial conformer, we have that 1,3 overlap. So what do we see as we get larger substituents? Like, for example, a tert butyl group. Well, it's a very large substituent, right? And so what happens to that interaction? It's a large energy difference, isn't it? This is going to be very unstable as an axial position. And the equatorial position is much more stable, isn't it? Okay? And we look here, and even if we have something fairly small, this does have some energy difference, doesn't it? Okay? So fluorine is just a little bit bigger than hydrogen, and so it has a little bit of energy difference. Okay? Okay. Anybody have any questions there? Okay. Now, an interesting side note to this is if you get something that's positive here, this can actually flip this energy difference and become more stable as axial. But that's not something you guys particularly need to know. Just a little, yes. If it doesn't repel and it attracts, this flips. Okay? Okay, so let's go ahead and talk about cis. Cis means on the same side of, right? And then trans means on different sides. Okay? And so right here we see the diaxial again. And in this case, though, instead of having a hydrogen on those diaxial positions, remember these positions right here? They were hydrogens, right? We have another methyl group. And so what do you expect to happen to that 1,3 diaxial interaction? They're bigger, aren't they? So you're going to get a larger interaction, more steric interference, right? Okay. And so this is highly unfavorable. You'd only have like less than 0.1% of your population in this form. Okay? This is a pretty big energy difference. This one's going to be much more stable. 99.9% of your population is in this form. Okay? And this is because this is the equatorial, which does not have a 1,3 diaxial interaction, right? These are both pointing out away from the ring. And you can't really see this as well here, but this one's pointing out away from you. Okay? This one's pointing out away from the ring like that, right? Okay. This is the trans 1,3 dimethyl. Notice here that instead of having these on the same side, the top side of the ring, we have one on the top, one on the bottom. Can you see that difference? It's not the conformation that's changed. This is an isomer change. Okay? So before we had tops, both of them, that was cis. That was an isomer. Then we had one on the bottom, one on the top. That's the trans isomer, right?
So it's not axial to equatorial.
Yeah, the axial equatorial is a conformational change. It has no bearing on the isomer. Okay? The isomer you can't change without breaking the molecule, reacting it, right? The conformation's flip-flopping all the time at room temperature. Okay? Does that make sense? Good answer. Okay. Yeah, I'm always going to ask you, by the way, whenever you ask me questions, if that answered your question, because, you know, I'm not you. You're not my little puppets, hopefully. Okay. Again, when you have the trans conformation, whatever conformation, well, isomer, when you have the trans isomer, whatever conformation you're in, you're going to have one in one direction, one in the other. Okay? So your one will be axial, one will be equatorial every time. They can never both be the same. Right? That's the 1,3 positions, by the way. And so you'll end up with axial equatorial or equatorial axial. They end up degenerate, don't they? Can you see that? Because no matter how you change this conformer, you always end up with one equatorial, one axial. So same energies. All right. Okay, so this one's the tert butyl. And right here we have the tert butyl on both sides. So we have it on the 1 and 4 positions. These are very large groups, aren't they? So what do you think is going to happen to our chair conformation? So if we have cis tert butyl, again, that's the isomer. They're on the same side, right? So they're both on the bottoms. Okay. So right here we have it the equatorial position, right? Is everybody comfortable seeing this? That's equatorial pointing out away from the ring. And so we get very little overlap with the 1,3 interaction. Okay? But the other side, we end up in the axial, don't we? And did you remember that energy difference for that axial on that table? It was the highest, right? It was very high. 20-something kilojoules per mole, right? And so what ends up happening is this interaction is so large energy that this actually is going to cause us to have the boat twist conformer as our most stable conformer. Remember, that's different than what it normally is, isn't it? It normally was the chair conformer the most stable. But if we're in the chair conformer, one of these groups has to be in the axial, which has the 1,3 interaction, doesn't it? Okay? And so what we've ended up doing is we've made the boat twist boat, the most stable conformer. Does anybody have any questions?
In this case, both the working groups are in the equatorial position.
They are, yep. So both the tert butyls are in the equatorial. The hydrogens are in the axials. Okay? Are you starting to kind of see it? Let me tell you, anybody that's having issues seeing this, don't feel bad and don't like, oh my God, this is terrible. I'm screwed. Seriously, get your hands on a model kit. If you can't afford to buy a model kit, come into the lab. I have model kits in the lab. Okay. When you physically manipulate them, your brain will start connecting. Okay. And this is one of the reasons I recommend most people need a model kit. Linus Pauling, the Nobel Prize winning chemist that actually figured out the structure for DNA, predicted it before they had experimental data, is actually said that you can't do chemistry without a model kit. So you have a Nobel Prize winner that says that. Gives you the perfect excuse to buy that model kit, doesn't it? Okay. Or come in and use it from me. All right. Let's go ahead and do some problem working. So go ahead and draw both chair conformations of cis-1,3-dimethyl cyclohexane and determine which conformer is stable. Then you're going to repeat this for the trans isomer. And then you're going to predict which isomer, cis or trans, is more stable. I'll give you 2 or 3 minutes, and we'll probably end up ending on this problem, okay? Really do draw it out. It works much better if you actually draw it physically with your hands. Okay? If you're extremely good at abstraction, there's actually programs I can recommend that will basically do what a model kit would do, but in a 2-dimensional program. They're not as good as the model kits, though. The model kits are definitely better and will help you more. So we're working on this problem here. Okay. So cis-1,2-dimethyl cyclohexane, draw that out for the 2 conformers and figure out which one's more stable. Then do it for the trans, and then predict which isomer, cis or trans, is more stable. An interesting side note that you can pretty well predict most molecules, but there are molecules your predictions would be absolutely wrong on. There's something called conformational studies, which is one part of what I used to do. Okay, let's go ahead and go on to A. All right, so remember we're doing the cis isomer. Cis means what again? Same side. So this means those methyl groups are going to be on the top of the ring, right? Or both on the bottom. It doesn't matter. Like if you do them both on the bottom, it would get the same result upside down, right? Okay, I would recommend drawing them out towards you because they're easier to see and understand. Drawing them off from the other side of the ring is more difficult, okay? So when you draw a ring, a 6-membered ring in line edge formula, make a triangle like that with one side that's towards you a little bit shorter. Draw 2 lines parallel off of that triangle and then connect the 2 lines with the triangle. The 2 lines, because this one here is going to be a little bit further out because it's a little bit closer to you, it's jutting out towards you. That line will end up ending a little bit further out because again, it's jutting out towards you. Okay? Okay, so What you're going to do next is you have to go ahead and put these methyl groups onto this ring. So because this is the top one, the head of the chair, you're going to have this methyl group as the axial. Okay? If you start trying to draw these in, you can pretty much do it very easily. Just put the bonds first before you put anything else. The bonds need maximum separation, which means they're in a V shape, right? Can you see the tetrahedral shape you're making? 2 V's? Okay. And that ends up in the axial position if you do that, right? There you go. That is going to have the methyl on it because we're putting the methyl on the top. The other one gets the hydrogen. Then what I'd recommend is doing the same thing here. Again, you need to make tetrahedral, which means 2 V shapes, right? One V shape is made by your ring. And then you're going to put another V shape, which goes like that. Right? Can you guys see my fingers going like that? Yeah, I make 2 V's with my fingers, insert them into each other, right? That's how this always looks. If you're ever confused, just take that shape with your fingers and line it up. And then look down it. See that? Okay. If you have a model kit, it's far easier. You can just make this and rotate it so it lines up with your paper. And then you can sketch it out. Okay? So model kits are very useful when you're starting out. Anyways, again, you're going to be on the top. So your CH3 goes here. Your hydrogen goes right there, right? Okay. And so that was my cis isomer. This one here has axial here. And this ends up being equatorial. Can you see how it juts out along the equator? Okay. It's actually jutting out towards you, isn't it? Okay. Does anybody have any questions so far? No? Okay. Okay, so when you're doing this, the other conformation is just going to be flipping both of those flaps, right? So right now, the right side was up, left side was down. I'm going to flip both of them. Okay? Okay. So this side's going to be up, this side will be down. Whenever you do this for the this cis right here, isomer, we're going to end up with them flipping the equatorial axial positions, aren't we? Okay? So the CH3 that was axial will now be equatorial. The CH3 that was equatorial will now be axial. Another interesting way to think about this is that when you have them right next to each other, so you have 2 carbons that are attached next to each other that have then methyl groups off them or whatever substituent. Okay? If they are cis, these cis positions, the same side positions, have to alternate equatorial axial. Okay? So, this is axial, up is axial, equatorial. Axial, equatorial. Axial, equatorial. Axial. Cool, huh? And that's for the 6-membered ring. Okay? Okay, so again, is everybody clear how we get this? Did anybody get lost anywhere? Anybody have any problems that they ran into? Fantastic. Okay, so in this case, we always have one equatorial, one axial, and that means their energies are, use your language, degenerate or equal, right? Okay. So your energies are going to be the same energy for both conformations for the cis isomer. Okay, now we're doing the trans isomer. The trans isomer, they have to be on opposite sides, don't they? Okay? So you make your 6-membered ring in the chair conformation. You put them on opposite sides, and what you'll end up seeing is you'll get axial-axial, won't you? Okay? And then you flip both of the flaps, and they both end up having to go equatorial, don't they? Okay. And that's actually the rule that I use there. The things on the same side have to be axial, equatorial, right? They're on opposite sides, and they have to flip, don't they? Okay? So if it's on the opposite side of the ring, then it would be axial instead of equatorial, right? This one right here? Okay, it's a little hard to see in 2 dimensions, but remember this is tetrahedral. So sort of take your fingers and point it into like this. This is your hand right here, right? And then those are your fingers going down, okay? And then take your other hand, and remember this is tetrahedral, right? Where you have them perpendicular to each other. So 2 V's with your fingers perpendicular, okay? And so what we see here is that the ring is like this. This then would be your CH3, right? So your hydrogen is up along the ring. Does that make sense? It has to be written weird because you can't write it right there. And your CH3 is actually jutting out towards you, isn't it? Okay? Like it's trying to poke you. And that's jutting out away from the ring. Or another way of saying that is it is in the equator of the ring versus this one is perpendicular to the ring itself's axis, the flat part of the ring. Did that help? Okay. It makes even more sense if you do a model. Okay? Model kits make this kind of trivial to figure out. Because literally as you flip a good model kit, the strain of the different model kit bars that connect things will cause everything to flip the correct directions. Because that's why they flip like this, right? Is literally the strain along that connection. Yeah. So model kits work really nicely. Did that make sense? Did I actually answer the question? Okay. I think I might have taken some circles there. Okay. So what we see here is that the trans isomer is kind of interesting, isn't it? So basically, both conformers of the cis isomer are the same energy, and they're both in that middle area, right? We have one axial, one equatorial, right? The trans one has the highest energy conformer, axial, but also the lowest energy conformer, doesn't it? Which is equatorial. Isn't that unique? Ooh, it's so pretty. Okay, did anybody have any questions? Did I lose anybody here? Okay, fantastic. All right, so what we end up saying is that the last part, our trans isomer is actually going to have the most stable one, isn't it? Okay? And that's right there, equatorial. And if we look back on our table with those 1,3 interactions for the methyl groups, what we can see is that we get about a 7.6 kilojoules per mole lower energy as compared to the cis isomer, which has one axial, one equatorial. Okay? Basically, we have one of those groups going from axial to equatorial. So one additional 1,3 interaction. Okay? Okay. There we go. And that's that. Anybody have any questions? No? Okay, this is the ethyl, by the way. If we have the ethyl here, we can see that the ethyl takes up more space. So if we substituted one of those methyls for an ethyl, what would happen? Well, the ethyl takes up more space, right? So it being in the axial position is going to be less stable, isn't it? You want the ethyl group in the equatorial position instead. Okay? And that's going to give you the more stable ring, the lower energy ring. the lower energy conformer. Anybody have any questions about that? Ooh, I won't. Okay, so we are doing okay. The bicyclic systems. So again, bicyclic, what do you think those mean? Yeah, like a bicycle, right? 2 wheels. Or 2 rings, right? Yeah. So bicyclic, 2 rings. There's some concepts that we need to introduce, so we have the language to talk about these. Now, this is actually kind of one of those places where geometry gets kind of interesting. It looks complex, but in reality, there's only 3 things that define all of these systems. Okay? It's kind of like knots. Knots have very few factors you actually have to identify, and you can then identify trillions of them. Okay? Same thing for the rings. And so we have fused rings. Notice this is bold, by the way. Bold means what? Important. And important stuff like these that are terms, you need to do what?
Highlight.
Memorize. Yeah, it's language you need to memorize because otherwise it doesn't make any sense for anything. Okay? Okay, and those are where you'd use flip cards, right? Okay. I'll probably not point that out anymore. So hopefully you got that down and start doing flip cards and get used to it. Okay? Okay, so fused rings are going to share 2 adjacent carbon atoms and the bond between them. This is an example of a fused ring. See that they share 2 adjacent carbons and that bond in between them, right? These rings are literally fused together, aren't they? Okay. Bridged rings. This is going to share 2 non-adjacent carbons and 1 or more of the carbon atoms, the bridge between them. So in bridged rings, they don't necessarily just share 2 carbons in their bond. Okay? It's going to be more like they have a bridge between them. Right? And then spirocyclic compounds, these are rare, by the way. There are 2 rings that share only 1 carbon. So they're going to connect in just 1 carbon. They don't share any bond between them, none of that. Okay? Okay. All right, so right here, this is the actual naming convention for bicyclo rings. So these are bicyclic compounds and how you name them. Okay? These 3 numbers altogether define all bicyclic compounds. Okay? All right, so right here, again, we have our bicyclic ring. In this case, it is what? It's a fused one, isn't it? Yeah. See that? It's fused. It shares 2 carbons with the bond between them. Okay. Okay, so we would name it according to this right here. So we go bicyclo to tell us it has 2 rings, right? And then we name the numbers of carbons on our bridges, each of them with the least number, going down in numbering. Okay? So our longest first, second longest, third longest, and that's it because we only have bicyclic. Okay? Okay, so for example, we look at this. The number of unique carbons in this, i.e. the bridge, is 1, 2, 3, 4, right? And so we put 4. We then put a period. The next one has 2 unique carbons on it, and so that is a 2-carbon bridge, right? Unique carbons being ones not shared. Okay? And then finally, we have right here the final bridge, which has 0 carbons in between it, right? Okay. We would name this according to the total number of carbons here. So how many carbons do we have here? 4, 2 here, 6, 8. And so that's an octane, isn't it? Okay. And that way we can always draw this back out. So to see this, we do 4. We put 4 carbons here, right? As part of a ring. Okay? And then we know the next one has to have 2 on the other side. And then we have 2 left, and so that means it has to have a fused. By the way, this right here means it's a fused one. It doesn't have any bridge right there, right? Okay. That you have 2 carbons that fuse this, that have nothing in between, just a bond. That's the 0. Okay, if it's not fused, you'll have numbers that are non-zero in all 3. Okay? So again, we have bicyclo. This case, our longest one is 3. And then we have 2 over here. And then 1 here. See that has 1 carbon in between those? Count the total number of carbons, and again, this is an octane, isn't it? Okay. Okay. In many ways, it's actually easier when you draw these out to start with the smallest number first. So what I typically do if I have to draw these out from a name is I would actually look at the octane first. I would write 8. Okay? And then I'd look 0. That tells me I have 2 with a bond between it. Right? And then from there, I'm going to connect those with 2 more carbons, which are going to be the 4-membered ring, right? And then from there, well, 2 of my carbons here have to have a bridge, which is then 4 carbons long. Okay? And that gives me this 6-membered ring over here. Right? So if you go backwards in these, it's easier to draw them out. Bicyclic means I have to have 2 rings. 1, 2 rings. 1, 2 rings. Can everybody see that's actually 2 rings? Okay. Okay. All right, very good. This is decalin. We have the cis-decalin and the trans-decalin. You'll notice that this actually gets defined by these hydrogen bonds. That's the easiest way to envision it. Okay? So these hydrogens are cis to each other. These are trans. It's always the hydrogens on the bridge head being where the bridges connect. Okay? So this is a bridge. This is a bridge, right? These have to be the bridge head. Can you kind of see that? That's like a bridge coming over the... Okay. This would be like the lake right here. Okay. If we look here, what we can see is the cis and trans. The cis is much more contorted, isn't it? See how it's much more trapped into that conformation? And it can't relieve its strains by rotating around as much. Can you kind of see that? On the other hand, the transdecalin is more stable because our alkyl groups here can have that normal tetrahedral arrangement, right? Where they can relieve that steric strain. Another way of saying that is they can adopt an equatorial. Okay? Okay. All right, so this right here is talking about primary, secondary, quaternary, tertiary, etc. Okay? So a primary carbon is only going to be attached to one other carbon. Okay? A secondary carbon would be attached to how many other carbons? Secondary means 2, right? So it's attached to 2 other carbons. Yeah. Okay. This is again a methyl carbon. So this is a tertiary carbon. How many other carbons is attached to it? 3, exactly. Notice the methyl carbon has how many carbons attached to it? None. It's methyl. Has no other carbons attached to it. Okay? And that's why it's referred to as a methyl carbon here and not as a primary carbon. You see, technically, both of those are methyl groups, right? One's attached to another carbon now. This one right here. Okay, so this one's attached to how many other carbons? 4, so 4 is quaternary. You got it. All right, let's talk about alcohols. Alcohols are not carbons. They're oxygens, aren't they? And so when you name an alcohol, you name it based on the carbon it's attached to. Okay? So this right here is a primary alcohol because the carbon it's attached to is a primary carbon. Can everybody see that okay? Okay. It has one other carbon attached to the carbon it's attached to, right? This right here is attached to a carbon which has 2 carbons attached to it. So that is a secondary alcohol. This right here would be a tertiary alcohol because how many carbons is attached to the carbon it's attached to? 3. Now, if you try to get confused on this, okay, notice that you can never have an alcohol with more than 1 carbon attached to it, can you? How many bonds does oxygen typically make? 2. If it's an alcohol, one of those bonds is always hydrogen. And so you can only ever have how many carbons attached to an alcohol? 1. Okay? If you start getting messed up on this, that should be a big hint. It's literally impossible to have anything but a quote-unquote screwed up primary, right? So it has to be the number of carbons attached to the carbon attached to the alcohol, right? Okay, amines are actually similar to the carbons because amines can have more than 1 carbon attached, right? Okay, so we have here a primary amine. That means the amine, the nitrogen, has 2 hydrogens, 1 carbon, right? Primary, 1. Here we have a secondary amine because how many carbons are attached to it? 2. By the way, how many bonds does a nitrogen want? Typically 3, right? And so that means that however many carbons are attached to it, that's going to reduce the number of hydrogens. Okay? Okay, this right there is then a tertiary amine. We have 3 carbons attached to it. That means we can have 0 hydrogens, right? All right, now amines are kind of interesting because they have one more thing we have to think about. We have ammoniums, right? Because amines are bases, right? So when it has something else attached to it and it gets to a 4 things attached to the amine, quote unquote amine, okay? When we have 4 things, that gives it a positive charge. That means it's a cation. And that means it's a polyatomic cation. Remember those from back in Gen Chem? And what was the polyatomic cation that had nitrogen in it? NH4 plus was ammonium, wasn't it? Yeah. And so this is ammonium salt. Okay? Back in Gen Chem, you would have done it as a salt, right? Ammonium chloride, ammonium hydroxide, whatever, okay? Okay. And so this is an ammonium salt. You can have ammonium salts with NH3 that are attached to a carbon. You can have an ammonium salt with an H4 plus, and then it's attached to like a chloride or something, right? Or you can have an ammonium salt that it has 4 carbons attached to it. Okay? Okay. In every case, it's a salt. It's going to come with an anion that's associated with it, right? Okay, by the way, this is very, very, very common in medicines. It also is very common in seafood. What makes a fishy smell? Amines. Amines are what make the fishy smell. Okay? How can you reduce the fishy smell and fishy taste of a food, of a fish? What do they always serve fish with? Not tartar sauce. Oftentimes they do not serve fish with tartar sauce. But they always serve it with lemons. Yeah, they always serve it with citrus, right? Okay. What is citrus? It's an acid, isn't it? What happens when you put amine, a weak base, with an acid? It's protonated, doesn't it? That gives you an ammonium salt. Okay. What sort of boiling points do ammonium salts typically have? Pretty high, right? Have you ever melted salt? Well, you dissolved it, but you haven't melted it, have you? Because salts typically melt somewhere in the 400, 500 degrees Celsius range. Okay? And they're very difficult to melt. You usually burn them first, if they have oxygen. And so the vapor pressure of those amine compounds, when you acidify them, becomes very low, and you can't smell them anymore, right? Okay? And that way you get the flavor, and it actually get more flavor because they dissolve very easily. Because salts dissolve easily, right? In water, like your saliva. So the flavor becomes more rich, while the smell of it is reduced. Okay? Neat, huh? You didn't think you'd get some cuisine, did you? All right, I guess we'll go ahead and just stop here.